Hi, I am Aditya NG and I will be presenting our work on using transformers to build efficient occupancy prediction networks for unstructured traffic scenarios. Existing approaches for vision-based depth estimation consist of estimating the disparity given a pair of calibrated stereo images, or estimating the disparity of a single image with respect to a virtual camera pair. When a system is trained to optimize for disparity, it is important to note that the error in disparity grows quadratically with distance. Another limiting factor is the large volume of data that is necessary to train such models. We propose our solution to these problems through our occupancy prediction network, OCTraN, and our dataset generation pipeline, which in combination provides a self-supervised training pipeline to generalize depth estimation to arbitrary scenes. OCTraN uses convolution to extract 2D image features. We apply iterative attention using the perceiver module in order to transform these 2D image features into 3D occupancy features, and then apply convolution transpose to upsample 3D occupancy features. By applying convolution on spatial data and using iterative attention to transform from one feature space to another, we are able to efficiently utilize the good inductive prior that the convolution operation has with respect to spatial data, while taking advantage of the flexibility provided by the transformer for transforming from one feature space to another. Also, since the loss function operates in occupancy space and not in disparity space, our model's error with respect to depth grows linearly and not quadratically. We run an ablation study on our network architecture. OCTraN B is our base model in which the transformer is tasked with extracting 2D image features and transforming them into 3D occupancy features. In OCTraN V0, we leverage a ResNet plus FPN feature extraction backbone to aid with 2D image feature extraction. This enables the transformer to focus on feature space understanding. Finally, in OCTraN V1, we associate each column in 2D image space with a cuboid in 3D occupancy space. Our study shows that the addition of the ResNet plus FPN image feature extraction backbone drastically improves the performance compared to our base model. Although OCTraN V0 achieves a higher IOU score than OCTraN V1 and appears to be learning better, the trend of the loss over epochs in figure 5 indicates the contrary. Here we have a visual of OCTraN in action. OCTraN takes the image shown on the top left as input and produces an occupancy grid as output. This is an example frame from the Kitty dataset. The LiDAR from the dataset is sparse, leading to gaps in the voxelized ground truth. It is interesting to note that the model prediction is dense and these gaps in the occupancy grid are reduced. Our system achieves an IOU score of about 34% on the Kitty dataset. In order to train such networks, we require ground truth depth information. For this, we propose a depth dataset generation pipeline in which we collect video data from a single camera. By applying monocular depth boosting techniques, we are able to acquire 3D maps for each frame of the scene. This enables us to acquire depth information for a scene without the use of time-of-flight sensors. We also experiment with neural radiance fields for 3D scene reconstruction. We trained Instant NGP on our forward-facing driving footage and found that it is able to produce a visually correct RGB scene reconstruction when viewed from the camera's original trajectory. However, viewing the NeRFs 3D reconstruction from other angles reveals that it has a limited understanding of the 3D scene. This indicates that too few input viewpoints are provided for the NeRF to correctly generalize to the scene. We applied NeRFs on the Kitty dataset and saw similar results. Note the ghosting effect in the NeRFs due to the presence of moving objects. We trained Instant NGP on multiple sections of the Indian driving dataset and observed that Though the 3D reconstruction looks visually correct along the original camera trajectory, upon further inspection, we see that the road is pretty cloudy and unusable, with many objects being deformed due to the lack of variety in viewpoints. As NeRFs weren't suitable in their current form for our use case, we opted to use monocular depth boosting for generating ground truth depth. And here are a few frames from our dataset, along with their corresponding depth labels, which were produced by depth boosting. Note that the points closer to the camera are labeled as brighter, and points further away from the camera are labeled as darker. To summarize, we have gathered a dataset of about 114 minutes of unstructured traffic in Bengaluru. We have augmented our dataset with our depth boosting pipeline to generate 3D depth labels. Finally, through our ablation study of our occupancy network, we achieve an IOU of about 34% on the Kitty dataset, which is comparable to current state-of-the-art architectures. Thank you for listening.